Number 5. I see Giselle, I see Jose, I see friends up front. Okay, so for the folks that are with me, did you already try this one last night?
Yeah.
Okay, some of us maybe tried it last night. So I've got e to the y is equal to xy, and I want to find the derivative. What are we going to do? From any of the folks that are with me, what are we going to do? What are you going to do, Jose? You're going to find the derivative on both sides. So what's the derivative on the left?
Y times dy dx.
I want to be careful. The way you take the derivative of e to the power, the way we take the derivative of e to the stuff power,
Bring the power. Oh.
it's e to the same power, right? With the derivative of the exponential, it doesn't change. The derivative of e to the x is e to the x. The derivative of e to the power of stuff is e to the stuff. Don't stop though.
Yeah.
Christian, can you get that? Times
dy over d.
Times dy dx. Now I've got to go over here and I'm going to take the derivative on the right. Knowing me, how are you going to find the derivative on the right? What would you do?
Product rule.
Product rule. So the product rule says take the derivative of the first part, 1. Leave the second one alone, plus the first times the derivative of the second. I know that my goal is to solve for dy dx, so anywhere that I have a dy dx, I want to get those terms on the same side. I hope the algebra of this is becoming more natural. Okay, so I'm going to say this is e to the y dy dx minus x dy dx is equal to y. Next move, Christian, what are you going to do?
Try to move everything up to the right.
Well, I want to solve for dy dx, and I think we have a problem.
You need to take them out.
You want to take them out. The word I was hoping you were going to use, the F word I was hoping for here, I was hoping that you were going to say factor, right? And I bet some of you guys, like the algebra is popping now, and you're like, oh, I know I'm going to factor and I'm going to divide, and maybe you don't show the factor out part. That's fine. So we're going to get that dy dx is equal to y divided by e to the y minus x. I factored the dy dx out. I divided by all the other stuff. And I'm done. Great answer. Where is it?
Nowhere. Not on
Sad panda. It's not there. Or is it? Who sees it? David sees it? This is fair game. We had this conversation at some point yesterday. Abraham's all excited. I can see. He sees it.
So we already gave you the e to the y.
They told you in the beginning that e to the y is equal to x times y. Which means anytime you see e to the y, I'm going to call that xy now. So that now what I've got is y times xy minus x. And that's going to be that final answer. I care greatly about our ability to find the derivative on both sides using the chain rule. Our ability to solve for dy dx. This last piece over here, we're just getting a little tricky. Getting a little tricky on the multiple choice. Questions on number 5? Any other ones that we need to talk about before the timer goes off?
Can you talk about number 4?
Okay, there's a request for number 4. Martir, what's your request?
11.
11. Let me check out number 4. If I look at number 11, they both involve sines and cosines, so I don't... 11's a little uglier, but let's look at number 4. All right, number 4. Sine of x minus cosine of y minus 2 is equal to 0. Who's with me on number 4? Okay. Eunice, you've been absent the last couple of days, right? So you're just yesterday. I missed you dearly. It felt like a lot longer. Sine of x minus cosine of y minus 2 is equal to 0. Same deal. I want to find dy dx. Jose, help me find dy dx here. What are we going to do?
So cos of x
Okay, so the derivative of sine of x is cosine of x.
minus negative sine of y times dy dx.
Oh, love. Negative sine of y times dy dx minus the derivative of 2. 0 equals the derivative of 0. 0. So cosine of x plus sine of y dy dx is equal to 0. All I need is some algebra. A little bit of algebra if I'm going to solve for dy dx. So I can subtract that cosine of x to the other side. And
Yes.
then
Divide
by the sine of y.
Yes.
Okay, so dy dx, I heard we're going to subtract that cosine of x. We're going to divide by sine of y. Is that one of the answers?
No.
Ah, I'm hiding it again. Where am I hiding this? How am I hiding it? I heard cotangent. Not in love with cotangent. Maybe there's some cosecant stuff. Edgar, tell me where you're seeing cotangent.
I thought that was like cosine sinus. Because I know sine over cosine is tangent.
Sine over cosine is tangent, but here's the problem. Here's the problem. Hold on, Giselle. I know you got it. Is it true that the cosine over the sine is cotangent? Yes, as long as
The variables are the same.
Oh.
the angles are the same. These angles are not the same.
Oh, one of
You
them.
can't reduce and say cosine over sine is cotangent when it's cosine and sine of different angles. What you could do would be to say, what if I write this as the negative of the cosine of x times 1 over the sine of y, and now 1 over sine of y, you guys should know is,
Cos.
careful, 1 over sine. It's cosecant. So this guy here is going to be negative cosine of x times cosecant of y. Done. Okay. Anybody get a perfect 10 out of 10 last night? 8 out of 10 or better. I'll take 8 out of 10 or better and feel good. Nice, we're in a good place. We're in a good place. So if you guys can make sure your name is on it, make sure you put how many you got right out of the 10 on the top of the page. Put that in the middle. If things are not going well for you right now in the land of implicit differentiation, including the home audience and anybody who has been on college visits, tomorrow during lunch, if anybody wants to just stop on by and spend some time on implicit differentiation, we can do that. Okay? So let's put that in the middle of the table. Edgar, if you wouldn't mind picking it up, I'd appreciate it. Reassessment opportunity today after school. We'll spend about 45 minutes to an hour working on corrections to the quiz. After the corrections to the quiz, you will take another free response optimization problem. Lots of fun. Lots of fun. Adriana actually stopped smiling yesterday in the middle of it. Interpret that any way you want. She stopped smiling and started, like, I don't know, sending the ugly boyfriend after me. So there's that. Okay, not ugly, I'm sorry. I mean that he's a good-looking guy. Okay. Some of you owe me the multiple choice or the free response portion of the trimester exam. You made the corrections, or maybe you didn't make the corrections and I just need it back. That would be a good thing to have happen. And Josue, I feel like I should have a moment of silence for him. It's been at least a week and a half since I saw his face. I miss him.
How are you carrying him back?
I miss him.
Stop.
All right. So, my friends, we are going on this evolutionary journey. I am so excited. Today's lesson has balloons, or I guess one balloon. One lucky person gets to inflate a balloon. But we are going to take our derivative rules and have one more evolutionary step in the chain here. So just like man and his computer have evolved from skinny guys with big computer screens to much narrower computer screens, your derivative skills have evolved. Way back, oh my God, this was so long ago, you may not even remember it was so long ago. We did really hard things like find the derivative of e to the 3x minus 2. Like find the derivative of 1 over, what is that, t squared plus 1? Mm-hmm. And we found the derivative of natural log sine theta plus sine natural log theta plus sine theta natural log of theta. There once was a time, believe it or not, those were the hard things. I want you to take 2 minutes completely on your own, go find those derivatives for me. Those used to be the hard things. They used to be the hard things. 2, 5, 8, 11, 14, 16.
Anthony Bennett. Oh, and Jenny.
Yeah, I got it. Thanks, sir. So I've seen a whole lot of papers. E to the 3x times 3 is the derivative of the first one. Nice little chain rule. We're in, we're out. Jennifer, what's your plan for the second one?
We have to take c squared plus 1 back to where the exponent was negative.
Oh, very cool. So you are rewriting as t squared plus 1 to the negative 1 power. How many of you guys did it that way? A couple people did it that way? How many of you guys did quotient rule? Quotient rule is probably the more popular approach, but both are going to be fine. If I do it this way, I'm going to say negative 1 t squared plus 1 to the negative 2 times the derivative of the inside, which is 2t, which becomes negative 2t over t squared plus 1, the whole thing squared. Great. And my quotient rule people, you should have the exact same thing. Because when you do your low, d high derivative of 1 is going to be 0, minus high, d low, that's going to be 2t. That's where this negative 2t comes from. Over low, low. Nice, we're good. All right, third one. Can I get some brave soul? What's the derivative of the natural log of sine theta? Natural log of sine theta. Edgar, what you got for me?
1 over sine theta times cosine.
1 over sine theta times cosine. I love it. Jonathan, how do you feel about derivative of sine of natural log of theta?
Cosine 1 over beta.
Okay, I want to be careful. I'm asking you for the derivative of sine of natural log of theta. Chain rule, right? What does the chain rule tell you to do? Derivative of the mama. Leave the baby alone. So let's fix it. What's the derivative going to be here? Cosine of the natural log of theta. So that was derivative of the mama. Leave the baby alone. How about theta? Theta, and then Adriana, how about derivative of sine theta natural log of theta?
Cosine
Yeah.
of theta
Cosine of theta
times the natural log of theta
times the natural log of theta
plus sine of theta
plus sine of theta
times 1 plus times 1 over theta.
times 1 over theta. How many of you guys are like, this is good? Jasmine, you're good? Everybody's fine.
Yeah.
Love it. Put a check mark on it. You've earned stickers. Then lately, we upgraded your skills. I upgraded your skills on Thursday. We started talking about implicitly defined curves. And Daisy, what does it mean if a function's implicitly defined? What do you know about the variables if it's implicitly defined?
There are 2 different variables.
Well, there's 2 different variables. There's 2 different variables here too. But there's 2 different variables
Next to each other.
on the same side.
On the same side.
Yeah, on the same side, right? Those x's and those y's are getting mixed in together. Jose, how are you going to find the derivative over here? What are you going to do?
2x
2x
plus 2y
plus 2y.
times dy dx.
And why are we doing that?
Because it's the derivative of y.
We're measuring how y changes as x changes, right? It's the derivative of y with respect to x. So it's 2x plus 2y dy dx equals derivative of pi squared?
0.
0, right? I want to solve for dy dx. No, you don't have to put a box around it, but I like to. Dy dx, I'm going to subtract 2x, I'm going to divide by 2y. And so dy dx is equal to negative 2x over 2y. Reduce if you want to. Negative x over y. If you've done this one, great. We're not going to worry about that. This is where we've been. We've been in explicit land. We moved ourselves over to implicit land. And now it's time to upgrade the skills one more time. You're either rubbing your hands together to stay warm, or because you're so excited about related rates. Because here's the really exciting part. Wait for it. It's all application problems. It's all geometry. Our favorite things in calculus is when we do calculus involving geometry and application problems. Could not be more happy about this. So excited, so excited. This is really creepy because you're following me every move I make. That's all right. That's all right. I can handle it. I will not crack under the pressure and start crying. No, not me, not anymore. All right. I used to. Back when I had a heart. All right. So, here's the thing with related rates. With related rates, we're going to measure how things change over time. The world, stuff, changes over time. If you guys were born and raised in Massachusetts along with me, we would talk about snowballs and what happens to a snowball over time. Because you are Texans, you have no idea what I'm talking about. But imagine, if you could, a snowball. I bring the snowball into the room. What happens? The snowball melts. Things are changing about the snowball. What's changing? The mass changes over time. The mass decreases. What else?
The shape.
Actually, the shape doesn't change that much. It usually melts on kind of like all the sides at the same time. The volume changes. The surface area changes. All these things change over time. This is a related rates question. We okay? Mm-hmm. All right, Christian. Blow into this balloon while Edgar reads the opening problem.
Is this the box one?
Yes. Oh, where it says notes on the hook.
Oh. Jose is getting ready for a birthday party and needs to inflate some balloons. He is able to blow into the balloon at a rate of 3 cubic inches per second.
Keep blowing, Christian.
When the radius of the balloon reaches 4 inches, determine the following.
Okay, so awkward. I have a Jose and I ask Christian to blow into the balloon. But Christian, why don't you deflate the balloon? Okay. And I want everybody to watch him while he blows up the balloon one more time. So you are blowing this blowing into this balloon. Make it happen.
I'm pretty sure I'm starting to go that.
So he's blowing into the balloon. What's happening to the balloon?
Expanding.
The balloon is expanding, right? Things are changing about the balloon. For example, what's changing?
Volume.
The volume.
Volume is changing. What else? Surface area is changing. What else? The radius is changing. Maybe you want to have a heat energy conversation. We're not going to do that. But is everybody okay? The radius of the balloon changes. Volume changes. Surface area changes. All these things are changing over time. These are related rates. You're good. You can let it go. All right. So here's how we're going to play the game. What do I know? What I was told in the beginning, you're blowing into the balloon at a rate of 3 cubic inches per second. That is a rate of change. What's changing? He blows into the balloon at this rate of 3 cubic inches per second. What's changing? This is a measure of what?
Volume.
Volume. How volume changes over time. We're going to express this as dV dt. I know you're used to seeing me write like dy dx, which is how y changes over how x changes. This is how volume changes over how time changes. So dV dt is going to be 3, units are important here, cubic inches per second. That's what that dV dt is going to represent. The volume is increasing or decreasing?
Increasing.
Increasing. David, how do you know that this is an increasing?
Because it's expanding at a rate of 3 cubic inches per second.
The balloon is expanding, and I'm going to indicate this by a positive over here, right? Part A, what's the volume of the balloon? This is where we're going to need some geometry stuff. Anybody know how to find the volume of a sphere?
times minus.
So funny. I think the answer is no.
No.
Good news. I'm generally going to give you the formula. So the volume is going to be 4/3 times pi times r cubed. Okay? Is this always the formula? For a sphere, is this always the formula?
Yes.
So this is an always true kind of thing? That's going to be the key. Things that are always true are going to be more powerful to us. If this relationship is always true, then I can use it no matter how big the radius is, no matter how small the radius is. So this first question is not even really it's not a calculus question. What's the volume of the balloon?
4/3.
The volume is going to be 4/3 times pi times 2 cubed. I've heard 4 cubed and I've heard 3 cubed.
4 cubed. This is the radius of the balloon.
Yeah, you got to keep reading. The radius of the balloon is 4 inches. Now, always true that the radius is 4?
No.
No, there is a moment in time, right? If Christian keeps blowing into the balloon, there is a moment in time where the radius is equal to 4 inches. That's the moment I'm focusing in on here. So at that point, the volume is 4/3 times pi times 4 cubed. And the units have to be, because this is a volume kind of problem, cubic inches. I heard cubic inches per second. What I want here is just straight volume. Not how volume's changing, just volume. And the way that you measure volume is cubic inches, not cubic inches per second. Okay? So let's do part B. I want the rate at which the radius of the balloon is increasing. That's a rate of how the radius changes over time. Here comes the new piece. This guy here has the units of a derivative. I want to treat it like a derivative. I can only take derivatives of relationships that are always true. So the one relationship that I know that's always true is this guy over here. Watch how we're going to take the derivative. We're going to take the derivative on both sides, but t is the variable. So the derivative of v is dv dt. It's how the volume changes over time. Is equal to, check out the derivative on the right, 4/3 times pi. I need the derivative of r cubed with respect to time. The derivative of r cubed is 3r squared, but I'm measuring this with respect to time. I'm comparing how the radius changes to how time is changing. So it's going to be 3r squared dr dt. I'll take questions on that in just a second. The key is to take that volume equation that you guys told me is always true, and find the derivative with respect to time. So it's like with implicit differentiation, when you had like a y, and you took the derivative, you'd write dy dx. I'm taking the derivative of volume with respect to time. So I'm going to measure this as dv dt. 4/3 and pi are constants. The derivative of r cubed is 3r squared times dr dt, because the radius and the time don't match. They're different variables. Jasmine?
I thought that if a variable is a constant, then it's 0.
If a variable is a constant, then it's 0. Okay, I think what you mean to say is if I'm taking the derivative of something that's a constant, then the derivative is 0. That's true. Is the radius constant? Think about the example. We've got Christian blowing into a balloon. Is the radius constant?
No.
Is the volume constant? Surface area?
No.
There's nothing constant there. Everything's changing, which is why I need to have this dr dt expression showing up. This is going to tell me how things are changing. Great question. Other questions?
Could you explain again how you got the dr and dt?
Okay, I'm taking the derivative of r. R is the variable, but I'm taking that derivative with respect to time. It's like with implicit differentiation, if this was a y, you'd say 3y squared times dy dx. Okay, so let's finish it off. We're not done. I know you guys want to be done, but you're not done. Not done because you actually haven't figured out the problem yet. The rate at which the radius is changing, what I want is dr dt. If I'm going to figure out dr dt, you better know all the other variables. Do we know dv dt? What's dv dt?
4/3 times.
Careful, what's dv dt?
No.
The value for dv dt is 3. It says 3 cubic inches per second. Equals 4/3 times pi times 3 times r. Do we know what the radius is?
4.
4.
Right, at 4 squared dr dt. Nothing but a little bit of cleaning up here. 4/3 times pi times 3. Those 3's can cancel. 4 times pi times 4 squared is 64 pi dr dt. If I divide, I'm going to get 3 divided by 64 pi is dr dt. So my radius is changing at a rate of 3/64 pi. I'm not interested or worried about this being a pretty number. That's not the thing. That's not the thing. But the radius is changing at a rate of 3/64 pi. Need some units. Radius is changing. Right? How do I measure radius? How do I measure radius? Inches. How do I measure time?
Seconds.
So this is inches per second. What this means is when my radius is 4 inches, right? The assumption here is that we're looking at when the radius is 4 inches, the radius is increasing or decreasing?
Increasing.
The radius is increasing at a rate of 3/64 pi inches per second. Kind of okay? Okay, here's what I want to do. I want to get out of your way. I want to give you guys some time to practice. We're skipping over part C for right now, because what I want to do is give you guys some practice with finding derivatives with respect to time. So if you look on page 3, there's a whole bunch of problems here. These are some of the geometry formulas you're going to run into while we're doing these problems. Between now and I'll call it 1:57, so you guys can get 10 good minutes, I want you to just focus on the derivative process. No word problems, no units, but find the derivative with respect to time. Whoever's birthday is closest to today, you are in control of the cups in honor of my 14-year anniversary with my wife. So you've got 10 minutes. Show me what you can do. Read these things carefully.
No. Why are you doing that thing? No, it's your birthday. Jose! When's your birthday? When's your birthday?
This is finding the derivative of r to
Brain attack.
Oh, I was mistaken last time. No, not even. March count.
Would it be 2
I mean,
times
December.
dA over dt?
So in the what we just did, only the
I'll put it in my calendar.
Well, the
March
volume
And
changes.
then with respect to time,
Sure.
Show me that
that's
problem.
what I think. I'm not sure.
so like that.
Unless it's a constant. But are these constant?
But you're assuming that all of these things are changing with respect
But
to
it's
time.
close.
So the derivative of a squared with respect to time is 2a.
Oh.
Because you are measuring how these variables are changing over time.
We're doing these. Find the
Yeah.
derivative.
So
How do we
the
figure this
derivative
out
is
then?
2a.
With respect to t.
We're just going to take the derivative of everything that's over here. A squared is 2a
What is
times
usually
dA
in
dt,
respect
just
of?
like we did with implicit differentiation.
Yeah, that's what I'm thinking.
Plus derivative of b squared.
2a
times
times
dt
dA over
equals
dt.
derivative of c squared.
2c times dc dt.
Huh? That's what he said, because he said with respect to t. So it's going to be 2a dA over dt.
Yeah, which one do you know? You just pick, I mean, there's 3 variables here.
Right. And all 3 variables are changing with time. They're all changing. Unless you're told in the problem that it's a constant. So the derivative of a squared is 2a. But a is changing with respect to time. Plus the derivative of b squared is 2b, but b is changing with respect to time. The derivative of c squared is 2c, but c is changing with respect to time. All the variables are changing over time, so they're all going to have a d something dt, unless you're told that it's a constant for some reason.
A is a constant, right?
Yeah, it's it.
Nothing is
Yeah.
0.
It is changed.
Yeah, that makes sense.
So what's the derivative of a?
Does it tell
Would it
you?
be 1? So we don't need to have the derivative of a. Would it be 1?
It is changing.
Towards the side?
So a would be the same as 1.
That's what I got.
So then 1a. We can pretend there's like a 1 down to a, so there's 1a. And the derivative of that would be
Well,
1.
oh no, wait. I mean, the volume. I mean, we had this.
Jonathan, for number 2, what did you mean? Why are you laughing?
Just going on tired.
Well, I don't think, for number 2, for a, would the derivative be 1? But why? Wouldn't a be the same as x?
Oh, it's 2. No. Has it been multiplying or is it together?
Oh, okay.
Yeah, like when you multiply x and y, it's like 1 to 1. You have to say that with respect to t.
Yeah.
So I'm like,
So I guess I just forgot.
Now you're adding them? Why are you adding them? Yeah, I was looking at that too. I just multiplied it. Oh no, yes. Well, are you multiplying it here too? I mean, this is a constant.
Yeah, it's constant.
But you don't
multiply.
change it.
It's a constant. You multiply. These are two variables.
You were.
because you didn't change it around.
So if anybody's still on number 2, I've got area equals pi times r squared. What are the variables? A and r. Those things are changing over time. The derivative of a? dA dt. The derivative of pi, which is a constant, times my radius squared, is 2r dr dt. Keep going. Because we always,
It's not changing when you're multiplying.
this is the same question. Right? What's the derivative of x squared? What's the derivative of x squared plus 5? What's the derivative of 5 times x squared?
No, it wouldn't be in front of him, would it? Because he didn't have it.
5 times.
Just let them.
Always
So it's
one
more
constant. If it's a constant that you're adding, that's when it becomes a derivative constant.
Dang, look at you. Good stuff.
Yeah. No.
No, they don't
It's
know
like
how to do
you've
this.
never heard of the product rule.
Yeah, but it has 3 variables.
So Jose, on this third one, how many variables you got?
3
And they are
A, L, W.
A, L, and W. So start with the derivative over here. Derivative of A
DA.
is dA over dt. The derivative of LW.
Oh, do you want?
The derivative of LW, that L and that W, what are they doing to each other?
Product rule.
It's multiplication. It's a product rule. You don't get to throw out old derivative rules just because you're learning something new. So dL dt times W plus L times dW dt. The one I want you guys to try number 8 and 9. Friends over here, how many?
And this product rule now?
Sorry, what?
And this product rule now?
Yeah.
Product rule again is that. Wait, product rule for R squared times H or for all of it?
I wouldn't type over my answer, but I'm still where I'm getting attention. Not I want to get happy and sad and attention, so that way I'm not disappointed. I'm just
Oh, that's true.
because I already want to be disappointed. So,
That's it. Is this correct, Mr. D?
So 1/3 I times 2r dr
Oh,
dt plus, now here's where you need to be careful. That 1/3 pi, I'd like to see everything after the 1/3 pi in parentheses, because you're saying it's 1/3 pi times that whole derivative. So 2r dr dt times h plus r squared dh dt. ddt 1/3 pi r squared h, you're multiplying those together, that's a product.
Parentheses just on those? Yeah. No, yeah, you're right. It makes sense.
All right, folks, I want to plug everybody together. Let's look at number 8 together. Number 8, volume equals 1/3 pi r squared h. My first question, how many variables? What are the variables?
2, 3.
3 variables. Things that are changing with respect to time. Jonathan, what's changing over time? Volume, radius, and height. They're all changing. No constants here. So let's find the derivative. The derivative on the left
dV over dt.
is dV over dt. That's how we talk about volume changing. 1/3 pi. David, what do you know about the 1/3 and pi? What do you know about the 1/3 and the pi? They they're constants. So what happens when you take the derivative of these constants that are multiplying the r squared and the h? We just had the conversation. The 1/3 and the pi, these guys are constants. They're constants that you're multiplying by. You ignore the constants. The constants come along for the ride, just like the conversation we were having about the derivative of 5x squared is 5 times 2x. So this is going to be 1/3 pi times the derivative of r squared h. Now the reason I'm going to write it this way for right now, the only way I can find the derivative of r squared h is going to involve a product rule. I'm not ready for product rule if I'm still struggling over here with the 1/3 and the pi. So just write it this way. Now let's go and find that derivative. The derivative with respect to t of r squared times h
2R.
So this is 2R
Times dr.
times dr over dt. Because I'm doing the product rule. The product rule says take the derivative of the first guy and then
times the second.
times the second
Plus
plus
the first.
the first, r squared, times
Derivative of the second.
derivative of the second. And the derivative of the second is
dh over
dh dt. And all that stuff represents the derivative of r squared h. So I'm going to leave the 1/3 and the pi there, and that's what this dv dt is. How many guys that honestly came up with that? Okay, got some folks. We're making some progress. All right, let's tackle another word problem. This one comes with a prop to help visualize here. March here, can you flip over to page 4 where it says model application problem? And read the introduction.
Sewing princess works up into climbing to the top of a 7-meter ladder that is leaning against a house. Slowly then started pulling the ladder away from the house at a rate of 1/2 meter per second. When the ladder is 5 meters feet from the base of the house, how fast is Princess Buttercup coming towards the ground? Be sure to indicate the appropriate unit.
All right, one of the things I would strongly recommend with any of these problems that involve geometry is take a minute and read through this, get yourself a good visual. Draw something that might help move you forward. So think about this situation. Don't spend too much time on the house. Don't worry, is it 2 stories? Is it 1 story? What are the things that you know? So hopefully your diagram looks something like that. We've got a house, or we've got a wall, we've got a ladder leaning up. What happens? What's happening in this problem, Giselle?
She's pulling the ladder.
Who's she?
Zoe.
Okay, Zoe. So
Away
we've
from
got
the
my
house.
dog Zoe, who's pulling the ladder, and she's pulling the ladder
Away.
away. So we're pulling the ladder from here. And what happens? Think about the reality of a ladder if you pull on the bottom.
It's gonna fall.
It's going to fall. Now, last year, some of the kids thought, wait, if the dog pulls on the ladder, doesn't the ladder just sort of come this way? It's like they've never studied this idea called gravity. If you are going to pull on the bottom of the ladder, the top of the ladder goes down, right?
Or just different type of ladder.
Or they use a different type of ladder, an anti-gravity ladder, maybe. So, I want to slide the ladder.
Oh.
Right, so in that case, she's pushing the ladder closer to the wall. She's pushing the ladder, she's pulling the ladder away from the wall. What's something that's always true? Are there any relationships here that are always true? Because those are the powerful ones. Jasmine, what's something that's always true?
The ladder is always the same height.
The ladder is always the same, I'd rather use the word length.
No.
It's always 6 meters. Anybody else know anything that's always true? Daisy, do you see something that's always true?
I was gonna say that the height of the wall is always the same, except it changes with the ladder.
Well, the height of the wall doesn't actually change. The wall is not changing here. Edgar, what's something else that's always true?
X is always positive.
X is always positive, so X is like the length. What else do you see that's always true?
It's always a right triangle.
You are always making a right triangle. Is everybody okay with that thought?
Mm-hmm.
How does that help?
Oh.
If you always have a right triangle, Jasmine, what else do you always have?
You can always use the Pythagorean theorem.
You can always use the Pythagorean theorem. So let me freeze this guy here. Thank you very much. That was wonderful. So let's add a little bit to your diagram here. So for my diagram, Here's my house, here's the ladder. You guys told me that this is, what, 6 meters?
Yeah.
So let's label this diagram. What else is happening?
Pulled
Zoe is
away.
putting it away.
She's pulling the ladder away. Now, I know that this guy is constant. This is always 6 meters, but the length here, constant or it changes? It changes, so I need a variable name for it. Use whatever variable makes the most sense to you, but I'm going to go with X. The height of the ladder, like height of the ladder above the ground, constant or changing?
Constant.
Change.
Oh.
The height of the ladder above the ground changes. Need a variable name.
Why?
Why? Because we've got a right triangle, I know that x squared plus y squared equals 6 squared, and this is always true or sometimes true?
Always.
Always.
Always true. When you have a relationship that's always true, that's the thing. That's the thing you're going to take the derivative of. Because that relationship's always true, we can look at how this relationship changes over time. So let's take the derivative with respect to time. The derivative of x squared is 2x, be careful,
dx over dt.
times dx over dt, because this is a measure of how x is changing over time. Plus, I need the derivative of y squared. 2y dy over dt equals the derivative of 6 squared. Oh my gosh, I was afraid somebody was going to say 2 times 6 times d6 dt. How about just 0? So that's the derivative. If I'm scoring this, it's probably 1 point for coming up with the original equation, 1 point for finding the derivative. What this question is asking for, though, is how fast is she plummeting towards the ground? Right? Because the dog has pulled the ladder away. So I've got the one dog pulling the ladder that way, and the impact is that this poor dog, Princess Buttercup, falls down. This is a rate. What was the value for the rate?
1/2.
1/2 meters per second? What that's telling me, though, is that something is changing at a rate of 1/2 of a meter per second. What's changing? Jose, what's changing?
I would say velocity or distance.
What's changing? If she pulls that ladder away at a rate of 1/2 meter per second, tell me what's changing. X is changing, so I'm going to call that dx dt. Dx dt is this 1/2 of a meter per second. What I want to know how fast she's plummeting towards the ground. What I really want is I want dy dt. I want to know what dy dt is. I know dx dt. I need dy dt. Fortunately, I've got my derivative relationship that connects everything together. So let's do it. 2 times, I need to know what x is. I need to know what x is.
5.
Is it 5?
It says when the ladder is 5
meters
meters.
from the base.
Okay, so when x is 5 meters, so 2 times 5 times dx dt is 1/2, plus 2 times y.
Right there, plug it in.
Marvin, can you explain that one more time?
You plug it into right there to find y.
We've got the Pythagorean theorem, which is always true, which means I can use this anytime I want to. If x squared plus y squared is always going to be 6 squared, and we're looking at this moment when x is equal to 5, I can go off on the side and say, oh, 5 squared plus y squared equals 6 squared. So 25 plus y squared is 36. Y squared is 11, and I think we've got y equals the square root of 11. I'm not going to worry about plus or minus the square root of 11 because that y represents a height. So my equation, when I put everything back together, 2 times 5 plus 1/2 plus 2 times the square root of 11 dy dt is equal to 0. Good news. The only thing you don't know is the dy dt. Take a moment to solve for dy dt. and figure out what the units are. I'm going to do y dt is negative 5 over 2 square roots of 11. Anybody else coming up with that? Okay, what are the units? What are the units have to be? Christian, what do you think those units have to be? Meters per second, because? We're measuring how the y changes. The y is the height. We're measuring how time changes. The time is measured in seconds. Why negative?
It's falling.
Because you're falling. If y is the height above the ground, shouldn't the y get smaller? So here's the final conclusion. I need a sentence. You've got to tell me, when is this true? When is this relationship true? When x, right, the thing that we knew was at this moment when x is equal to 5 meters. So when x equals 5 meters, what's happening? We'll say PB falls to the ground. PB for Princess Buttercup falls to the ground at a rate of, need that rate, 5 over 2 square roots of 11 meters per second. Tonight's homework, there's, I think, 5 problems on the back. I want you to pick 3. Is it 5 problems or 4 problems?
It's 5.
5, okay. Pick 3. I've already sent you guys the solutions to these. With tomorrow being a half day, we're not going to have time to actually check the homework and do all the other things. You can stop filming at this point. Okay.